Hello everyone. Today I wanted to give a couple brief examples showing the central limit theorem and how it pertains as our sample size increases when you have distributions that aren't normal distributions. So the examples I'm going to do are a binomial probability distribution, a geometric probability distribution, and the Poisson probability distribution. So first we're going to start with our binomial distribution. So if we look at what I have here on R, I've got the n for my binomial, meaning that I'm doing 10 trials for this binomial probability. And I have a probability of success for each trial of 0.5. My mean, or my expected value, is n times p, and then the sigma 2 represents the variance, sigma squared. And this is just going to be n times p times q. So I'm going to run each of those. And then what we're going to do is that when we actually are running this binomial probability is that we are going to do this experiment 30 times. And then what I'm going to do is I'm now going to sample doing this set of experiments, these 30 binomial probabilities. I'm going to do this 10,000 times, right? So right now, if I were to go and do the binomial, you would see that for the first one, I got 6 for the first 10, let's say call them coin flips, 3 for the second, 5 for the third, 1 for the fourth, so on and so forth. And then I'm going to do this 10,000 times, so meaning I'm getting 30 numbers, and I'm going to figure out on average what those numbers are, and I'm going to simulate this and do it a whole bunch of times. So I'm going to do 10,000 simulations, and then I'm going to create a histogram. Now, I did not create a seed, meaning that every time I do this, I will actually get different results. So the first time I do this, this is what the outcome looks like, my histogram, from doing those 10,000 simulated binomial probability experiments. If we were to overlay a normal distribution, you can see that this is actually pretty good at describing what's happening as my sample size, and I repeated this experiment over and over again, increased to very large numbers, in this case 10,000. And of course, if I were to do this command, this is just going to overlay the actual density function that represents this probability distribution. Now watch, I'm going to show you though, by doing this step again, I will actually get a different histogram. So this isn't something that I set up, so it just happened to work out specifically because of the seed I had set. So now I'll create it, and look, I have another normal looking histogram. I'll put my actual normal distribution over, and you can see that it still pretty accurately describes it. Let me do it one more time. And you can kind of see each time we're doing it, it does look very normal. Of course, if I were to do this simulation 100,000 or 1,000,000 times, this would be even more closely lined up with a normal probability distribution. So next we're going to look at is we're going to look at the geometric probability distribution. So in this case, we're going to use a probability of success of 0.3. We know that from our geometric probability distribution, the mean or expected value is going to be 1 over p. Our variance is going to be 1 minus p over p squared. And again, we are going to take 30 samples for each of these experiments. And then again, if I were to go and run one of these RGEOMs, which is the outcomes of my geometric experiment, oops, I forgot to add the +1, this will give me the actual outcomes. So in the first experiment, my first success was on the first term. The second experiment, my first success was on the second term. My third experiment, my first success was on the fifth term. My fourth experiment, my first success was in the third term, so on and so forth. And every time I were to run this, I'm going to get different numbers because each time it is randomly selecting from these parameters that we did for a geometric probability distribution. So now what I'm going to do is I'm going to simulate doing this 10,000 times, and I'm going to create a histogram. So here's the histogram to my geometric experiment. And then I'm going to overlay my normal distribution, and you can see that it's fairly accurate. Now it's not perfect. You can see that on the left side here, we are definitely undercounting a little bit. On the right side, we're overcounting a little bit. If we were to continue, because remember, the definition was as n approaches infinity. So this is an example for 10,000 simulations. If I were to increase this, it would get closer and closer. Let's do the experiment again though. Let's start by getting a new set of simulations, and we're going to create a new histogram. Okay, this one looks a little different. And you can see that, again, about the same amount of accuracy of looking like a normal distribution. We'll do one more. And each one you can see that even though each of these geometric probability distribution histograms are a little bit different, they all look roughly bell-shaped and mostly symmetric. The last one we're going to do, actually one last thing, I did add this rug command so you can kind of see where the actual values are happening. This actually would probably need something like what's called a jitter, which would allow us to see sort of a density around each point because each of these lines could represent one or thousands of outcomes. The last thing we're going to look at, though, is the Poisson distribution. Now, we didn't cover this one in class, but the way it works is it's a discrete probability distribution and is reliant on the parameter lambda. It is specifically used when you're looking at events that don't occur very often, so rare events. So we're going to set up using a lambda of 4. Again, we're going to have n equals 30, and we're going to do 10,000 simulations. So in this case, if I were to look at what the outcome is for my Poisson distributions, the first one was 5, 0, 4, 2, 4, 3, 4, so on and so forth. If I were to do it again, I get different numbers. So each time I do this, I'm getting different numbers. So now what I'm going to do is I'm going to sample this, and I'm going to create my histogram. And you'll see again that it looks pretty normal. Every one of these examples that I have done are discrete probability distributions. We know that they are not normal. And yet, when I did these experiments with sampling 30 from each distribution, and I did this over and over and over, 10,000 times each, you will notice that the outcomes begin to form a normal distribution. And this is an example of the Central Limit Theorem at work. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.